Okay, can you see my screen? I think so.
Yes.
Okay, great. Okay, so let's begin today's lecture. So I'm going to give you a lecture on variational autoencoders, and I was planning to give you a brief introduction about myself and what I did, but Mahesh already did that. So I would be skipping most of the points here. So before I finished my PhD, I was at IOE Pulso campus doing my electronics and communication engineering. Over there, with some of my friends, we did this thesis about vehicle overspeed detection and recognition. And this was one of the starting point for myself to get into this amazing world of machine learning or AI. So my general research interest that was also explained by Mahesh. So I'm interested in machine learning, and within this, I am interested in topics like disentanglement, semi-supervised learning, and generalization. And in terms of application, I am interested in how we can use AI in biomedical domain, especially around medical imaging and genomics. And recently, with some of my colleagues at Stanford, we have started this newsletter to cover the recent research around application of AI in biomedicine. So if you are interested, please sign up to this newsletter. Okay, now let's move on towards our session today. So these are the outlines of our today's lecture. So I'll be first discussing about autoencoders. Then I would like to briefly explain about the generative modeling, but I guess you already have received a very in-depth lecture on generative modeling, so this should be fairly straightforward for you. And then with the introduction of generative modeling, we would try to look into the variational inference, and these topics would then naturally lead us to variational autoencoders. And in terms of applications, I will try to briefly explain some of the application, and among them, I would try to give not detailed, but still good explanation of disentanglement. And in between, along the way, if time allows, we would also try to see the demo. And for the demo, I have written some codes in Python and PyTorch. Even if you are not familiar with these languages or frameworks, I hope you pretty much get the ideas of what we want to achieve. Okay, so let's move on towards our topic first. First, we will discuss autoencoders. So since you already have received one whole week of schooling about machine learning, I guess autoencoders already came somewhere along the way. So I would like to point out that autoencoder, first of all, is simply a type of neural architecture. You might already have seen CNN, which is also a type of architecture, or RNN or LSTM, which are also another type of architecture. And within the types of machine learning, we usually try to divide machine learning into different learning paradigm. One is supervised, another is unsupervised, and another is reinforcement learning. So I would like to place autoencoders within the unsupervised learning paradigm, because here we do not require the annotations of the data set. But still, there are cases or research that are happening where autoencoders are also being used for supervised learning or even reinforcement learning. So different components of autoencoders basically include encoder and the decoder. So here, as you can see in this pictorial representation of autoencoder, that we start with some input, and then we pass it through a stack of neural networks to get into this code, and then use this very same code to reconstruct back our input. So there are two major functions. One is the encoder, which tries to transform our data into some low dimensional latent code. And then we have another function, which is known as decoder, that tries to transform this latent code back to the data space. Now here, since we do not have our X and Y or our data and the labels, you might be curious what's the use of autoencoders. So some of the reasons on why autoencoders were initially considered and how it has been used in machine learning research includes, first of all, compression. So similar to how we compress audio files to MP3 format or images into JPEG format, autoencoders can very well be used to compress our data set into a small representation so that it can be used to transportation or sharing or to understand different aspects of the data set. And then another concept that has been quite popular these days, especially with the rise of deep learning, is the representation learning, where we try to represent or where we try to learn some abstract representation of the data set. So autoencoders are extensively considered when we want to learn such representation from the data set. And third, which would already be quite obvious, is to reduce the dimensions of the data set. So we often work in a setting where we have this high dimensional data set. And by the way, this dimensionality of the data set is growing every day because we are now considering even heavy data set like a satellite imagery. So in such situation, having an algorithm or a technique that can reduce our data set without losing much of the information would be very much useful, and autoencoders can be used in that setting as well. By the way, Mahesh already told us, so if you have any questions along the way, please feel free to stop me, and we'll try to address if there are some confusions along the way. Okay, now this introduction about autoencoders, if we have to represent it in some mathematical notation, then we can consider that our data set be X, and then with some function, let's say Q, which have a parameters phi, we can encode it to some latent code Z. So that means our encoder is represented with this notation, that is Z equals to Q of X. Similarly, we have another function P with the parameters theta to decode our latent code back to the data space X hat. So the expression of the decoder would be this X hat is equals to P of Z. Now, we have these two set of parameters phi and theta, and the in autoencoders, we try to learn these parameters simultaneously by minimizing the reconstruction loss LR. Here, the reconstruction loss LR is basically a measure of discrepancy between our input X and its reconstruction X hat over the training samples. Now, you might be curious, how would we measure the discrepancy between the X and the reconstructed sample X? And it largely depends on the type of the data set. For instance, if your data set is bounded, you might even use loss functions like cross entropy, or in general situation, if your data set is unbounded, then you might consider a mean squared error as shown here. Now, with this introduction, I would like to bring up another topic, that is the concept of regularization. So although we discussed about autoencoders and how we want to train autoencoders was by minimizing the reconstruction error, but in general, different research, they often include extra regularization. So the reason to use this extra regularization is that if we do not have any extra regularization, the autoencoder can learn some suboptimal solution, and they can simply duplicate our input features with the perfect reconstruction without having extracted any meaningful features. Now, to address this particular problem, if you notice in our earlier slide in this figure, let's say, we have reduced our input, this high dimensional input, all the way to this low dimensional bottleneck. So by just having this architectural system where we are reducing high dimensional data set into a low dimensional latent code, we already have this regularization in hand. Without having such bottleneck, the autoencoders could have learned simply an identity function, but by having regularization, we have stopped that. But here I am actually referring to some extra regularization, and some examples include, for instance, if you want to learn sparse features, then you might consider sparse autoencoders, or let's say if you want to learn a latent code which are insensitive to changes in the input, then you might consider the autoencoders like contractive autoencoder and denoising autoencoder. Since today we are going to talk more about variational autoencoders, I am not going into the details of these specific autoencoders, but the main message that I wanted to give you through these few slides was that whenever we are considering an autoencoder, I would encourage you to think about a loss function like this, where you first try to minimize a reconstruction error, and then there is another regularization term that you would consider depending on what sort of a problem you want to solve. So the main takeaway from this particular portion of our discussion is that we have autoencoder, which is often trained by minimizing a reconstruction loss between our original input X and the reconstructed input X, which we get by first passing the X through some function Q of phi, which would give us a latent code, and then passing that latent code to another function P theta that would give us reconstructed input. And as I said, and in most of the cases, we use some extra regularization beside this reconstruction loss. So this is the main takeaway that I would like you to take from this portion of our session. Okay, now let's move forward. So now I would like to move on to generative modeling. So we are completely changing the tracks here. So so bear with me on this one. And I know that you already have received a very extensive lecture on generative modeling, so I would not bore you again with the same details, I hope. And I would like to only start from the intuition here. So in generative modeling, the basic intuition is that we want to generate some data. If we want to denote it with X, so let's say we want to generate some data X. Now, the data set could be a collection of images of mountains like here, or the collection of some signals like electrocardiograms in this group. So if I were to ask you to generate some images of mountains, or to or in other words, if I were to ask you to draw something, then how would you have done it? If I were to imagine that, I would first start with some shapes or the colors, and then draw some background, and maybe then only I would start to fill in the details. So in the same way, we can think of those attributes as the attributes of imagination. So for the image, those attributes could be, as I just said, shape, colors, size, the background, and so on. For the signals, it could be quite difficult to imagine, because it has certain physical meaning behind these signals. For instance, these signals are what we get when we attach the leads in the body, and the shape of heart or shape of our body and the underlying disease would give rise to these signals. But in any case, even these signals have certain attributes. Now, these attributes, they are known as latent variables. So the idea is we have these attributes, latent variables, and then there is certain function that give rise to our data set X. Now, to represent this in a mathematical way, we have a data X, and then we have a latent variable Z. And we have this generative process where we first would sample our Z from some prior distribution P of Z, and then use that sample to our conditional distribution where we have P of X given Z. Now, since we have involved latent variables, this would naturally lead us to a latent variables model, which is a joint distribution of our data X and a latent variable Z, and it can be factorized in this way. Now here, I would like you to maybe take a pause and think about it. So when I introduced about generative modeling, I only demonstrated to you, or I only put the pictures of the mountains, but I do not, and I asked you to imagine the latent variables. So what I want to say is, we have a data X that is observed, but we have the latent variables that is unobserved. So, and then we said that our generative model involves generating data from Z. So the question, the natural question here is, where is this latent variables coming from, or where can we get that? And the answer to that question is, in order to get access to the latent variables, we have to rely on the process called inference. So in inference, the goal is that we want to infer good values of the latent variables given this observed data set, because eventually we can use those latent variables to do the generation process. And there are different ways to look at this inference process, but I would like to take a very simpler route. And for that, I am putting the Bayes rule in front of you. I hope this is very understandable, since we have been looking at the Bayes rule even in our stat courses. So in Bayes rule, we have this expression where we try to calculate the posterior using this expression, and over here, this px is the most important for us. This would be evident in few slides ahead, but in this slide, what I would like you to grasp or take is that we have this likelihood function p of x, which is this expression of integral px given z and pz of dz. So what we are essentially trying to do here is we are marginalizing out or sum out the effect of our latent variable z. So using this Bayes rule, we have p of x, which is like this, and then we have our prior pz, and then the conditional of x given z. So it sounds nice and simple. With this, we obtain our latent variable z. But the problem here is we do not know how to solve this integral function. Why we do not know is the relation between the z and x often has this nonlinear relationship, and even sometimes when this is solvable, we often deal with a situation where we want to work on a large data set. So this would become computationally expensive as well. So in general, this integral function that we require to get our latent variables is intractable. So when this px is intractable, this would make this whole thing intractable. That would now we require something that can help us solve this intractability. And for that, I would like you to take into another nice concept known as variational inference. Okay, so what exactly is variational inference? So the variational inference is, or the idea of the variational inference is that we want to model the true posterior distribution pz given x, which why we want to model is, I guess, has become quite obvious, because we want to have this generative model. And then since we were unable to get pz given x, we kind of accepted the crux of the problem, and then we are okay to use some simpler distribution. Let's consider it as qz given x, which is often known as a proposal distribution or also variational distribution. And we are using this qz given x with some simpler that is very easy to evaluate for us. And whenever you think about some distribution that is quite easy to evaluate, I am pretty sure that the Gaussian would come into your mind, because it has this mean and variance. We have a lot of analytical expression associated with the Gaussians. So we accepted that there is a problem, and then we accepted some approximated solution to use this qz given x to solve the problem that is in our hand. Now, at this point, you might be curious. We do not know PZ given X, and we decided to use this QZ given X. But how do we know how well we are approximating this unknown PZ given X? And for that, there is this concept of measuring the divergence, or in other words, we want to measure how well our variational posterior QZ given X is approximating the true posterior. And for that, we want to use this divergence known as Kullback-Leibler or Kl divergence. It basically measures the information lost using Q when we want to approximate the P. And the mathematical expression of Kl divergence looks something like this, where it is the integral of Q and the product with log P by Q. I guess you have another lecture afterwards on generative adversarial networks. Over there, you would probably learn about another divergence known as Jensen-Shannon divergence, which has some association with the Kl divergence as well. So the takeaway message from this particular portion of the lecture is we were stuck in a problem where we were unable to solve this problem of inferring the true posterior of the latent variables, and then we decided to use some proposal distribution to solve that. And in order to measure how far we are from that true distribution, we decided to use the measure of Kl divergence. Now, since we are here, I would like to maybe give you a very brief demo on the Kl divergence, because it has some nice properties. And for that, let me go here. Okay, is my this collab visible? Okay, great. So, so yeah, as I said in the beginning, I am using Python, and all of these codes I will put that in the assigned Google Drive folder. So you do not have to try to note it down or do. Oh, can you zoom it a little bit? Okay, okay. I hope this is more visible now. Okay, great. So here I want to give you the demo of the Kl divergence, and for that I am using this SciPy stat Python library. It's fairly straightforward, so I'm not going into the details of what each of these expression mean. So this cell, I just loaded some libraries. In this cell, I am defining my data space. And then the most important part is this cell where I am defining a distribution. And I define it as a Gaussian distribution. The notation for the parameters is different because they have not referred it as a mean and variance, but they use the location and scale. But let's not get into the details. Let's just understand that I have defined a distribution P, which is a bell-shaped Gaussian, as you can already see in this figure. So this is my true distribution. Now, in this slide, what I want to do is I want to define another distribution Q, and I just want to change the location, or I just want to change the mean. So when I do that, I am assigning this index, which is coming from these two for loops. So even this is not very important, but basically I am saying that this Q would be changing over time. And in the first instance of my loop, since my index would be 0, the location would be exactly same as my true distribution, the one that I defined before, that is 0. But then afterwards, this location is going to change. That's why I want to see how my KL is changing. So I calculated the KL between P and Q, and I see that in my first case of this for loop, I have a result as 0 because both distribution P and Q were exactly matching, but then it start to get increased. So this shows that how KL measures the distance or divergence between the two distribution. Now, another important thing about the KL is, although I just said it measures the distance, I would encourage you to not use the term distance, because whenever we think of a concept as a distance, we usually associate that if I measure the distance from X to Y versus if I measure a distance from Y to X, both of them are equal, right? But in KL divergence, this is not true, because the KL is asymmetrical. That is, if we measure from P to Q and if we measure from Q to P, it would result in a different thing. And to see that, I saw that I have defined P, and then I have defined Q, and then you can see that the result for these two things from P to Q and Q to P would come different. Okay, I hope this asymmetrical part is also clear. Now I have written this code for the visualization. So basically I am placing the green as our true distribution, and I'm only moving this red that I consider to be Q. And we see that as I move this red towards the green, the KL divergence get reduced, and eventually when both red and green matches, the KL is equals to 0. Okay, I hope this short demo was helpful. Okay, let's go back to our slide. Okay. Okay, so yeah, we now understand that KL we will use, or we want to use KL divergence to measure the divergence or the gap between our true posterior and the approximated posterior Q. Okay, now we had this problem where we had this likelihood function. We were unable to solve this because it has a lot of issues that lead us to intractability, and that affected our ability to capture the true latent variables. That's why we went to the variational inference. Now I would like to show you how we can use the variational inference to solve the problems at hand. So we start with this integral problem, and then we append or add this proposal distribution both on denominator and numerator. So this should be fairly easy to understand. Then I would like to take log on both sides, on both left hand side and the right hand side, and I have doing a bit of arrangement here and there. So as you can see, I just move the QZ given X under PZ, but this is fairly straightforward. Then this might be a bit confusing. Then what I did here is I took this log inside the integral, and to do that I am relying on this inequality, which is known as a Jensen's inequality, which explains that the log of integral is greater than equals to the integral of the log. So that's why my equals to sign has now become the greater than equal to sign. Okay, now once I use this inequality, I will try to do bit of changes inside the log. So what I did here is I guess this property of log is clear. That is, when we have a product inside the log, we can split it into two groups as the sum of logs, and when we have this division, we can split it as differences between the logs. So I am basically dividing this expression into two groups based on the log. And then we now have these two integral expression. And then if you notice, this second expression suddenly becomes familiar to us. It actually now resembles the expression that we showed before for the KL divergence. Here it's an integral of Q log Q by P. So now we can replace this by the KL term. So in total, our final expression becomes the log of evidence is greater than equals to to this first expression minus the KL term. And I have changed this first expression that was the integral to the expectation, which should not be very confusing, because we use integral for the continuous and expectation to usually denote the broad spectrum. Okay, so this final expression, which I have referred as a variational lower bound, is going to be very important in the consequent slides that we would be looking at. And this derivation should be, if there are any confusions in this derivation, I would be happy to take your questions. If not, we can move forward. Okay, I hope that this was pretty clear. Okay, so using variational inference, we were able to solve this, the integral problem that was lying in front of us. Okay, I see a chat message here. Okay, so this variational lower bound is also sometimes referred to as an elbow or evidence lower bound. So whenever you see these different terms, don't get confused or try to associate them to be similar thing. So this expression is basically what we were able to derive in the earlier slide. Now I would like to give you some notes on this particular expression. So, the two notes that I would like to draw your attention is that the first note, you might be curious, or even if you are not, we started with a problem where we wanted to use Kl divergence to measure the gap between the true posterior and the approximated posterior. But in this lower bound, this Kl term is not that particular thing, because here, as you can see, that this Kl is actually measuring the gap between the approximated posterior and the prior. So you might be confused on where that Kl term went. So to answer that, if you would have taken a different route and then derive it in a different way, then you would reach to this conclusion where your log P of x is equals to the elbow term plus the Kl term that was the initial motivation for us to begin with. This is also something I would like you to take a pause and try to absorb this. Okay, so and when you have understand this point, this point A, then this would naturally lead us to point B, because the Kl, which measures the divergence, is always non-negative. So that means that when you maximize this elbow term, this would naturally mean that you are minimizing the Kl term, because the evidence is not going to change, right? You are only modeling your latent variables, or you are approximating your latent variables. So the better you approximate it using elbow, that means you are trying to minimize that gap between the true posterior and the approximate posterior. Okay, and to take this concept in a more schematic way, I would like you to leave with this like a scribble, or the scribble of the plot that should give you the concept of what I just said. So we had this green curve, which was our original log P of x, and then we approximate this very complex phenomenon with some simpler distribution, and then we model it, but still we see that there is this gap that we were unable to fill in, or the better we model our elbow, this gap would be as close as possible. So this is very important concept in variational inference, and there has been a lot of research, or even when you want to dig more deeper into this topic, you would definitely come across a situation where you would better want to minimize this gap as much as possible. Okay, now we have introduced these topics. Now this would lead us to the main algorithm that we wanted to discuss in today's lecture. And the background of variational autoencoder in terms of how we went there, we already covered. But in terms of who introduced it, it's a very interesting story, because the variational autoencoder actually came out in parallel from these two papers, pretty much about the same time. So this autoencoding variational Bayes came from a completely different group. And then another paper known as a stochastic backpropagation and approximate inference in deep generative models came from entirely different groups, but both of them were explaining the same algorithm. And the first one was published in ICLR, and the second one, I forgot to mention here, but it was published in ICML. And I am using this quote because I really like how the authors write this quote. This is actually from the second paper. So they say that variational autoencoder marry the ideas from deep neural networks and approximate Bayesian inference to derive a generalized class of deep directed generative models. And here, I would like you to notice at these two terms. So the first one is deep neural network, and the second one is approximate Bayesian inference. So for the deep neural network, you can understand the concept of autoencoders that we discussed in the earlier portion of our lecture, and the approximate Bayesian inference would be the ideas from the variational inference. So as I just said, the perspective of variational autoencoder, I would like you to try to get it from both sides, that is the probabilistic and deep neural networks. So from the probabilistic perspective, it's a generative model where we want to generate X from some latent variable Z, and at the same time, we do inference from X to Z. And from a deep neural networks perspective, we have this data X, and then we pass it through some encoder, which are the layers of neural network, to get our Z, and then use the same Z to decode it back to the input space X hat. Okay, as I said in the beginning, when we derived this expression, that this is going to be very important, so I am bringing it again. So this evidence lower bound, or the variational lower bound, is basically the objective that we want to solve for the variational autoencoder. So here, this QZ given X is our encoder that would encode our data X into a latent representation Z, or in other words, or in the jargon of the probabilistic language, we are doing the inference of Z given X. And the schematic from the deep neural network perspective is what we showed before as well. And then there is another term that is Px given Z, which is a function to decode the latent representation Z into the data space X, or in other words, it generates our data X given Z. So in the holistic view, or in totality, variational autoencoder is the combination of encoder and the decoder. And here the objective is to minimize the reconstruction error and some regularization. So if you remember, when I was discussing about autoencoder, I was giving you this general takeaway where autoencoders are trained to first minimize the reconstruction error, and then depending on the problems at hand, we would add certain regularization. So from that point of view, you can say that autoencoder and variational autoencoder are the same, but it's only the perspective, because we just see that we arrive at these two algorithms in a completely different way. So here, the minimization of reconstruction error, or our LR, is represented by this first term of our evidence lower bound, and the regularization is represented with this second KL term that we have here. Now I'll try to go into details of these things. Okay, so in variational autoencoder, we have these different components. So the first component that I would like to introduce is this Q phi Z given X, which was our way to approximate the true posterior. So we are using a multivariate Gaussian with a diagonal covariance to approximate our true posterior. At this point, you might ask, or you might argue that, no, I don't want to use a multivariate Gaussian. I would like to use something else, some other distributions. Then the answer would be yes, you can do that. There are so many research that are actually doing that. But when variational autoencoder was first introduced, they started with this simpler distribution. And here, the mu and the sigma square, the parameters of our Gaussian distribution, they are basically the outputs of the deep neural networks. And then I would like you to draw your attention to this this generative model, that is the x given z, which we use, which we try to model using the Bernoulli or multivariate Gaussian, again depending on what sort of a data set that you are using. For instance, if you are using MNIST a data set like MNIST, which is bounded, then you might want to use maybe Bernoulli, or if you want to explore the whole variance from the data set, then probably you would want to use multivariate Gaussian. So it all depends on the data set in this case. And then for the PZ, which is the prior for our latent variables, we are using the multivariate Gaussian via the standard isotropic Gaussian, which has a mean 0 and the covariance as an identity function. Now, the interesting thing about the use of isotropic Gaussian as a prior is that the Kl divergence, this term that we have here in our elbow, between a multivariate Gaussian and isotropic Gaussian would become very straightforward, a very easy analytical solution. So here, as you can see, I am taking a KL between Gaussian, which has parameters mu and sigma square, with the isotropic Gaussian. So the solution, as you can see, is very easy. We can, if you think from an implementation point of view, you should be able to write a code pretty easily. And this is not just about writing code, but also in terms of optimization, it becomes very easy to solve. So we are trying to use everything that is very easy, and we can model the algorithm so that we have a very less difficulty. Okay, so in this slide, we now understand what is how we are modeling our Q, how we are modeling our P, and what is our PZ. Now I would like to give you the structure that would naturally lead from our previous slide. So here we started with X. We have some stack of neural network. It could be non-linear, like a multi-layer perceptron, or it could be CNN if you are using an image data set. It could be RNN, anything. It depends on the problem. But then after the encoder, you approximate, or you try to capture the mean and the covariance of your QZ given X. Once you have the parameters of that distribution, you sample your Z, which is your latent variables, and then you pass this sample through the decoders, which again could be multi-layer perceptron or CNN, and then you arrive at your reconstructed sample X. Then you would use a loss function to minimize the reconstruction between this X hat and this X, and then you would use your KL term to minimize the divergence between the QZ given X and PZ. Okay, everything looks nice. But everything is not nice. I actually wanted to say that, but by first introducing about this concept and then wanted to say you that it's not fine. Why it's not fine is, in this flow of VAE model, the random node, this one, the one that I have colored as gray, this random node or randomness, this is happening inside the model, which means that for the backpropagation, which we need in deep neural network training, we need to differentiate with respect to this random sampling. And in general, when we deal with the deep neural network, this is not possible, because we cannot backpropagate through this sampling node. instead, while proposing the variational autoencoder, the authors, they proposed this solution, which is famously known as a reparameterization trick, where the authors, they try to make this randomness that was presented in this way via the epsilon, and this is happening not within the model, but this is happening actually outside the model. So with this, we do not have to worry about learning and hence calculating the gradients for the epsilon, because we basically treat it as a fixed stochastic node. It's still stochastic, that is, we are still getting the randomness, but it's fixed. Now we would only learn the mu and covariance, and then we have this nice analytical equation to get our latent variables. So in this way, we have this two perspective or two part to do the optimization, one where we need learning or where we need to calculate the gradients. And over there, we do not have any sampling node so that the gradients can pass through the model. And then second, there is this stochastic node which is fixed because we do not want it to change over the time. And we are happy to keep this as a constant. Okay, so I would like you to probably absorb this a bit, because this is really, this was actually the major innovation when the authors proposed variational autoencoder, because beside that, most of the things was already lying there. They just added the pieces and then this particular trick that give rise to the variational autoencoder. Okay, since I do not see any question, I am assuming that this is fairly straightforward to you. Okay, now this would lead us to some sort of a pseudo code. If you want to think how would one implement this idea if they have to write a code. So I would like to draw your attention to this train function. So as you can see, I first start with capturing the X, or I basically sample the batch of data set from my training loader, depending on if you use PyTorch or Keras, the notation may be different. Then I pass this X to some encoder module, which would give me two things, the mean of Z and the log of variance of Z. And then I sample the noise, that was the epsilon in our earlier slide. And then using these approximated or these parameters of approximated distribution, I calculated the Z of a standard deviation. And then I have this analytical form for my Z. Then I pass this Z to a decoder function to get the X hat. And then I have a loss function to calculate the loss for the variational autoencoder. So in this way, using these few lines, we arrive at a, we can implement a variational autoencoder. Now, if you would like to see what this loss function looks like, then I have passed these four different terms as an argument. The X was the original input, X hat was the reconstructed input, and then this Z mean and Z log var were the parameters of our approximated posterior. And you see that I first calculate the reconstruction loss using some measure of discrepancy. Here I am considering the mean squared error. And then I am using the KL loss, which I pointed out a few slides back, that because we are using this KL between the multivariate Gaussian and isotropic Gaussian, it's very simple to calculate that. And then my total loss is the summation of the reconstruction loss and KL loss. I hope this is clear. If not, I would be happy to take questions here. Okay, I hope this means it's clear. But I would really like you to, yeah, when I was first studying about variational autoencoder, there was one important question that I had when I would look into this pseudocode, was that why would someone try to get the log of var? Why they are not getting just the var? Or why, since we started, if you remember, whenever I am drawing you the picture of this variational autoencoder, this or that, I always use the mean and this variance because these were the parameters of my approximated posterior. But then every time when I look at the code, the people used to write a code that would give them log of var. So this was very confusing to me. So if you did not notice, I will try to explain that, or if you already know, it would just be a revision to you. So we often try to capture log of var because you see that the variance, this would be always positive, right? Because variance is a square term and we cannot have negatives in the square term. So by capturing the log of var, we are allowing our neural networks to model however it would like to model our data. And then with log var, we can simply reverse it to get the variance. So that was quite interesting to me. Anyway, I hope this is now clear to you as well. Now with this, I would like to go into another demo that I have written. Okay, so this is now, as before, I would try to zoom in. Okay, so the framework that I have used to write this very basic implementation of variational autoencoder is through PyTorch. So please accept my apology if you do not use PyTorch and use something else. Okay, let me try to see if, okay, it's not giving me, but anyway, I have the result. So here in the first cell, we are loading the libraries. And in this second cell, I am loading the data set. Here I want to demonstrate the algorithm through the MNIST data set. So I'm basically loading them. Then I have defined my variational autoencoder as a class in this function. So this would be more interesting to us. So here, as you can see, these are the layers in the encoder, and these are the layers in the decoder. So what's happening here is I start with my input dimension 784 because I would widen my MNIST signal, which is 28 cross 28. I would flatten them into 784. Even this part is not important, so forget about it. But anyway, we start with the input signal that was of 784 dimension, and then reach to a lower dimensional input space, sorry, lower dimensional hidden space of 400. And then we are using two parallel layers that would give us our 400 dimensional hidden representation to some Z dimension where I use 20, where I can use 20 or whatever you would like to pass into this class. So this is the layers that are involved in the encoders. Now, in the similar manner, you can expand your Z dimension to a 400 dimensional vector, and then from 400 to your final input space dimension. So these are the layers that are involved in the decoder function. So your forward function would look like whenever you pass your data into a model as X, you would first get mu and log var. Then you would do some reparameterization to get your latent samples or latent variables Z, and then you simply pass that latent variables to the decoder to get your reconstructed input. So this series of codes should be fairly straightforward. Now, if you'd like to understand what each of these functions are doing, it's also simple. I'm basically just using those layers that I defined earlier to get my parameters of my approximated posterior, that was mu and log var, and my reparameterization also look like what we just discussed in the pseudo code. Okay, so I hope this code is very easy to understand. And then in this cell, I am defining my model and my optimizer. Now, in terms of optimizer, you might have seen or maybe already learned different optimizers like stochastic gradient descent or the variance of SCD. So the Atom is also one such variance and is often considered with the variational autoencoder. I'm not going into too much details, but if you are curious and want to use stochastic gradient descent here, I would you are welcome to do that, and I bet your result is not going to change a lot, at least in these demonstration purpose. Okay, then we have a training function, which is again the extension of what we just saw in our pseudocode, and you see that I have this loss function where since we are using the MNIST, I'm using the binary cross entropy and not the mean squared error, because it's bounded and I can get better result with the binary cross entropy. And then the KL loss term, which again I have said it too many times, that since we were using a KL between the approximated posterior, which was from a multivariate Gaussian, with the isotropic Gaussian, it's really easy and comes into this nice analytical formation. And then our total loss function is basically the combination of this reconstruction error times plus beta times the regularization, which is the KL loss. Okay, then this is the train function, which, as you can see, I sample the data, then I pass this data to a model to give me reconstructed samples and the parameters of my approximated distribution, and then I calculate the loss and then back propagate them. Okay, I think this would also be easy to understand. Then we have this test function where I'm just analyzing how my test loss would look like. Now, unfortunately, I was unable to load them right now, but I did pass this collab to a quick training, and I have trained it for about 100 epoch, but you can play around with it. I'm not going to train, and this may not be very important. Okay, now consider that we have trained our model, and as you can see that the loss values, if you see at the test set loss, it was decreasing, so we can assume that the model did train nice and fine. I can definitely make it better, but it should be good enough for us to look at the result. Okay, now here I would like to visualize how well I did the reconstruction. So so here I basically sample the data and then pass it through my model to do the reconstruction, and then I concatenate the tensors and then made a grid, and then doing the using IM, so I am visualizing them. So these parts are just technical details that I assume that all of you have a very good coding skill and it should be very easy. So you see that on the top row, these are my input signals. And then on the bottom row, I was able to do the reconstruction by passing all the signals through this small bottleneck of, what did I use? Yeah, through the small bottleneck of just 10 dimensions. So this is, if you think it, this is really interesting, right? Because by just utilizing this 10-dimensional latent vector, you were able to reconstruct your input almost perfectly. Because the dimension of these input signals, they are very huge compared to that 10-dimensional signal. So this is very interesting properties of autoencoders or variational autoencoders. Now, if I were to give you a demo of variational autoencoder, sorry, just an autoencoder, then I would probably stop myself on this cell. But since we are looking at the variational autoencoder, which is also a generative model, we can look at the generative property of the variational autoencoder. So for that, I get the epsilon, which is basically a standard noise. And then I pass this noise to do the decoding. So I am just starting at a noise and then passing it through my decoder, and I can think this process as a generative process. And then when I do that, I see that the model is generating, for this particular noise vector, the model is generating something like this. You might say this looks almost like a noise. This is or someone may see this as a digit 8. Feel free to put your imagination, but the point here is that the model is trying to learn something. It's trying to generate something here. Okay, we have some other things as well, but I would come at them again after we discuss some other topics as well. Okay, now let's go back to the slide. Okay, so I hope the pseudocode and the subsequent the PyTorch code was helpful for you to understand, and even if you want to later on go and try to implement this yourself, I would definitely leave the code. But I think that even without the code, if you have the concept well understood, then this would be very easy. The variational autoencoders is really easy to implement. The complexity may arrive depending on your data set. For instance, if you want to model some high dimensional image data set, and maybe the architecture that we draw in that code may not be enough to capture the complexity of the data set, but those things are something that you can start to add or play around, but the general concept is what we just covered. Okay, now let's try to look at the application of variational autoencoders. So whenever we used to talk about deep generative models, that is the generative models with the help of deep neural networks, the GANs or generative adversarial networks that all of you are going to have a very nice lecture in a while, the GANs always used to come before in terms of the ability to generate very quality samples. And the VAE always used to lag behind. Only recently, the VAE are also being used to generate these high quality samples like GAN. And as you can see, I took a snip from this particular paper, which came recently in 2021. And as you can see, the pictures over here, they are photorealistic, and I actually reduced the size. Even if I would expand the size, you can still see the details in the facial expression. So this is really nice achievement that variational autoencoders are starting to gain in recent times. Another application is semi-supervised learning. Since the very initial years when VAE was proposed, it was subsequently used to learn algorithms like semi-supervised learning, where we have labels for a very limited samples, and then we have this large group of unlabeled samples, and we want to use the latent structure learned by variational autoencoder to generalize my supervised or semi-supervised model to the unseen test data set. And then another nice application, and my personal favorite, is disentanglement. In our today's session, I would like to go a bit more into this topic of disentanglement. And there are a lot of papers that has been out in terms of disentanglement. I would also leave out with some recommendations as well. Okay, so now you might be curious, or like naturally you might be curious to know what exactly is a disentanglement, or in other words, how do we define disentanglement? And the unfortunate answer to this is that even now, even till date, the researchers in this topic still have not arrived at a very well-accepted definition for disentanglement, the well-accepted mathematical definition for disentanglement. But for a starter, like our today's lecture, I would like to describe disentanglement as the ability to learn a factorial latent representation that have this statistical independent variables. So in our previous demo slide, where we have this 10 where we define our latent variables as a 10-dimensional latent vector, those 10-dimensional vectors would be my Z0 to Z10, or sorry, Z9. So the latent unit that I want to be independent are among these particular units. So if we have to go back to our earlier discussion on generative modeling, where we started with this collection of the images of mountains, then our ability to learn a disentangled representation would mean that the attributes that would give rise to this mountain are captured in each latent unit. So if I wanted to have a generative model with, let's say, 5-dimensional latent vector, then my first latent unit would be capturing the shape, then size, color, and background color. Now, you might be curious, what's the use case of this, or what does this mean for the general AI, right? And then the answer is, if we really want to achieve that, let's say, the AGI, or commonly known as artificial general intelligence, then we need to have the ability to understand these concepts from the data set, and disentanglement learning is actually giving us the ability to do that. And in terms of application, what does this mean is, for instance, if you were to find out that your 4th latent unit have captured the background color for the mountains, that means if you would change only this background color, then I could probably get an image of this Mount Everest with the black background instead of this light sky background. So that ability is really phenomenal in the AI system. Now the obvious question is why we are discussing disentanglement in this variational autoencoder session. So I would like to give you probably a very brief introduction of why VAE promotes disentanglement. We can go really deep into this topic, but I'm not going to do that. So if you remember, when we were writing a code, or when we were thinking about implementing our variational autoencoder, we approximated the parameters of our approximated latent variables, or the QZ given X, using the mean and the covariance, right? So if you imagine the 2-dimensional latent variables, we had this Z, and then this Z is coming from a sample of a distribution whose parameters are the mu and this diagonal covariance. Here, the covariance matrix, they generalize the notion of variance to multiple dimensions, right? And by having this diagonal covariance, we are essentially learning a structure with the variance of our each unit to be independent to one another. Further, in this setup, since we associate our approximated posterior with this isotropic Gaussian, whose covariance again is an identity function, this further encourages all the dimensions of our latent variables to be independent. So this structure that we are using in VAE is already facilitating us to learn independent features, or in other words, disentangled features. However, different researchers, or even if you later go on and try to play with the code that I have, you would notice that it's not that really easy, because your VAE does not have this KL term alone as your loss function. You have this giant reconstruction loss in your first term. That means for any vanilla VAE or standard VAE, the learning disentangled representation is not good enough, because the other factors, primarily from the reconstruction errors, would be so powerful that it would hinder our algorithm to learn independent features. As such, one of the pioneer work in connecting variational autoencoder with disentangled representation came in 2016, about 2 or 3 years after the VAE was first introduced, and this work is known as a beta VAE. The nice thing about this work is they actually only added this beta in front of this KL term. And if you remember all our discussion about autoencoders, we always discuss that it has this reconstruction error, and then it has this regularization loss. This regularization loss can be weighted through some beta parameters. It was all associated with this beta term, but nobody added the beta term in front of this KL term before this particular paper. So what this paper proposed was that if we use some beta hyperparameters greater than 1, this would increase the strength of this KL term, hence giving us more freedom to learn independent features. Now, it's very obvious that if you increase the strength of this term, it would naturally mean that you would be decreasing the strength of this term. And hence, this paper, what they found out that if you want to learn a disentangled representation, then you might have to pay the price of reduced reconstruction capacity. Now, there are papers that have tried to mitigate this reduced reconstruction error despite learning good disentanglement, but we are discussing about this paper at the point in 2016 where if you want to learn a good disentanglement, you have to pay the price of reduced reconstruction error. Okay, I hope this this general introduction of disentanglement was somewhat clear. Even if not, we will try to look at this disentanglement from the pictorial representation. So for that, I would like to bring out this GIF. This GIF is of a data set known as D-sprites. So what's happening in this GIF is it's combining a lot of different images. So you already see or already notice that this data set is a collection of these small figures within this black background, where you see the changes happening in terms of shape. You see the changes happening in terms of rotation angle. You see the changes happening in terms of position of this little figure in your X direction, in your X direction or in your Y direction. Yeah, as you see that it's moving down in Y direction and X direction. So basically this data set has all these factors of variations in the data set well grounded up. So people who do research in disentanglement, they often consider this sort of a data set because they would now know how well they can do the disentanglement. So if you think what disentangling this particular data set would mean is that I would reach at a latent variable where each unit in the latent variable would capture a different attributes. It should capture the shape independently, it should capture the size independently, and so on, the position of X, position of Y, and so on and so forth. So the result, I am picking out the result from this beta VAE paper. So here, for a particular model that they train, they used, I guess, 10-dimensional latent vector. So you see that for their Z2, the third latent unit, has captured the position Y latent variable. So you see that this little dot is when you traverse a single latent values from 3 to -3, you see the changes happening only in your Y direction. So these little dots, it's moving upward only in this position Y. Now, in the same way, their Z6, the sixth latent unit, has captured the variation across the position X. So you see that this little dot is moving in the X direction and its Y position is basically fixed. And in the same way, we have this Z1 that has captured the scale, and then this Z5 and Z7, they have captured the rotation, and then there are other latent factors which are unused. So the main takeaway that I would like you to give is that whenever we think about disentanglement, we are thinking about latent vectors where each latent unit is capturing some independent features. And to see that, we can do this sort of a traversal experiment and find out which latent unit is capturing what feature. Okay, some other application within disentanglement include change, like a face picture, like image of a face, where this particular paper has a lot of different examples. And I picked one such example where when you change a single latent variable, you can introduce a glasses in a person's face. That means that particular latent unit has captured the variation across the glasses. In the similar way, this another paper demonstrated how a single latent unit captures the rotation across the digit, or how a single latent unit can have the ability to remove the colors from the color from these colorful digits. And similarly, another paper where they have this data set where they capture the wall color, floor color, and so on and so forth. So depending on the problems, depending on the data set, you can have disentangled models where you can capture the basic concepts in your data set. Okay, but here I would like you to give another quick demo that I have paused when we were discussing about our VAE codes before. Okay, so here, what I would like to do is, although I have trained only a variational autoencoder and not the beta variational autoencoder, I could simply have done that by, if you remember, the loss function that we wrote here. Yeah, so here I use the argument of beta equals to 1. So you probably want to play around by changing this beta value to maybe 5, 10, or however you would like. So by doing that, you would probably notice a more disentangled features. But in any case, even though I have trained only variational autoencoder, I would like to show you the code snippet that would help us to analyze how we can do such traversal experiment. So here I am doing this traversal experiment, which is also sometimes referred to as a latent walk, because I'm trying to walk in a latent space. So here I am doing that for all the Z dimensions. That is, we have 10-dimensional vectors. So I want to do the latent walk for each dimensions, because only by doing that, I would know which latent unit has captured which factor of variations. And then I define a vector which is similar to my epsilon, which was my noise. And then here, up until here, this is just defining that latent traversal that I want to do. And at the end, I pass this latent vector to my decoder, or to my generative model, to get my reconstructed. Sorry, here we are not talking about reconstruction, because we did not start from original X. Since we started from the noise vector, this is my generated signal. So for different changes in the latent representation, I would try to capture how it would generate the images back. And then here is one such example where, by changing only one latent unit, I see it has captured something. I'm not sure what is this. It's not as clear as what we saw in the result of the papers that I put in the slides, but we know that it is changing on something by only changing that one latent unit. You might argue it's trying to form a digit from some blob, or you might think that we started with a noise in this latent space, then we walk into a space of the latent structure where it has now started to give a more clear structure of digit 8. Now I could do that for my whole Z dimensions, right? We have a 10-dimensional, let me reduce the size. Yeah, so I can do that for the whole 10-dimensional vector. So each row here represent a change happening in only one unit, and there were, since 10 units, I can draw 10 such rows. Now if I pick, let's say, one random example, so here, let's say I'm looking at this row. So here I see that for some reason my generative model has learned for this particular latent unit to to swing from digit 8 to digit 4 by changing that only one latent unit. And similarly, if I look into this one, I see that there were some 4, and then it went to 8, and then again back to 1. So in general, is this disentanglement? I would say no, it's actually entangled, because we see that in different latent units, the factors of variation across digit class, that is the ability to represent different digits, is being entangled with other latent factors. So this is not good model to understand disentanglement, but it still demonstrate how we would be able to analyze disentanglement. Okay, I hope this would make the concept of disentanglement a bit clear to all of you. Okay, so with this, I would like to leave out with some recommendations if you want to dig down deep into this topic of disentanglement. If you remember, when I was bringing out the topic of variational lower bound, I said that there are so many ways to derive those equations. You would, even if you randomly search in some search engine, you might find out different ways to solve that. And this was one such paper that further dig down and dismantle the elbow that we derived earlier, and demonstrated how the elbow has so many different terms, where if you pick one term versus another term, you might reach at a completely different models. So these are some of the papers that could be very important if you want to learn more about disentanglement. Or if you want to discuss, if you went to this paper and get confused, want to discuss, I would be happy to chat about them offline later on, even after this school. Okay. Now I would like to summarize what we just learned in this lecture. So in the beginning, we started with the discussion about autoencoders, where we find out that autoencoders basically tries to reconstruct my original input by passing through some latent bottleneck. But depending on the problems, I could use different regularization to that. And we took a pause over there. And then we jump and did a quick introduction of generative models, and that led us to the problems of how we do not have access to the latent variables, and we want to approximate what we do not have. And to approximate, we discuss about the concept of variational inference, which is basically to use a separate, simpler distribution to approximate the true unknown latent variables, the distribution of latent variables. Then these two concepts, that is the concept of autoencoders and the concept of variational inference, they lead us to variational autoencoder, where we saw in that demo, we draw the reconstructed samples and how it's not so difficult to write a code about variational autoencoder as well. And then we also discussed a bit about disentanglement, where we try to see how we can analyze how well we have disentangled the latent space. With this, I would like to conclude this session. I would thank all of you for your attention. If you ever want to discuss any of these topics or any other research topics that are relevant to my own interest, you please feel free to contact me in any of these mediums. With this, I would be happy to take any questions if you have. Thank you. Okay, I think I saw one question here. So I would just rephrase the question here. So Mahesh asks me that, could you please mention ways in which variational autoencoder might help supervise learning problem in limited data setting, such as medical imaging, where you might have healthy and abnormal subclasses, and there are relatively fewer abnormal samples. Wow, that's in itself is a whole research topic here. But anyway, so I would like to split this question into maybe 2 or 3 different groups. So one of the ways in which you can think variational autoencoder in a supervised setting is that. For that, I would actually like you to go back. Yeah, maybe here. So you see that in this structure, I started with X, and then I try to reconstruct my my original X. Now, what if I have a problem of my X, and then I have some labels? Let's say I have this images of X-rays, and then I have a labels of it being either healthy or normal, or either it being unhealthy or abnormal. That is, I have a access to the labels Y. Then maybe I could use another structure where I start with X, use the very same structure, and then instead of doing the reconstruction, I would try to learn the label Y, right? We can see that it can very well be done from X to Y instead of from X to X hat. So we just made our variational autoencoder to some supervised learning algorithm. And if you'd like to know more about it, you might search about the algorithms like variational information bottleneck. So they try to propose the algorithm in a same variational autoencoder structure where we go from X to Y. Now going back to the question of Mahesh, so since we have this ability to go from X to Y, and then if I want to have a semi-supervised structure, that means I would, for all the labeled cases, I would go from X to Y, and then I have Z. And then for all the unlabeled cases, although I can go from X to Y, but since I do not have the labels for those unlabeled samples to do the supervision, I could use some techniques in semi-supervised learning, like ensuring that my hidden or latent representations are consistent regardless of the data set. So if I use such techniques, then probably the answer to your question would be yes, I can use the VAE in this setting of how you explained that in the problem of medical imaging. I'm not sure if my answer was helpful. Okay, yeah, I see the thank you. So I hope it was helpful. Okay, so I would go here if just in case if you have not used this.
The audience in the hall, please feel free to ask. Maybe there is a mic that's being passed around. Yeah. Great.
Okay, I guess we do not have much questions here, and that's completely fine. Some of the topics over here would require some more readings. Even when I first started learning about variational autoencoders, I had to probably go down, like read the papers, read the tutorials a couple of times, and that's true for not just the VAE, but any of the topics that you have been learning in this school. So I would keep this slide in our shared folders. You can go through it maybe this evening or maybe after the school, and if you find out any confusions in some places of the slides, I would be more than happy to answer them later on whenever you have time. Okay, I think I saw another question. Is there an automatic way to find out which latent unit is describing which features, or we always do latent walk? Wow, that's very very good question, especially for someone like me who have been working on disentanglement. So this question is something we try to tackle ourselves, me and my PhD advisor, a long way back, and unfortunately we were not able to do that in terms of automatic way. But latent walk is not just one of the, let's say, manual way. We now have so many metrics which would at least tell us how well we are doing the disentangling, or how well my, let's say, latent unit 1 is independent to my latent unit 2. So there are ways to tell me overall how good I am doing the disentanglement, and in specific how well I am learning the independent features. But what this particular feature is capturing in terms of our latent attributes is something it's still we do not have the clear ability to do that. I hope that was helpful, Mahendra Singh Thapa. Okay, yeah. Okay, I guess then that's it for our today's session. I wish all of you the very best for this learning experience. You still have so much great topics from amazing researchers. So yeah, I would wish you all the best. And as I mentioned before as well, if there are any questions about the VAE and disentanglement or anything related to my research that you would like to know, please feel free to email me and we can discuss more again. Thank you so much.